Welcome to the new advent of Cyber 2023. Cyber Monday. It's not quite Monday, it's Thursday. Thursday, December 14th, 2023. And this is a really cool song, by the way. This is a rare call in winter, which can hit you right in the feels if you're not careful. Task 20 today, day 14, machine learning, the little machine that wanted to learn. I think this is going to be a whole lot of reading for me, isn't it? Oh dear. Okay, so this task I had to do a little bit of preparation on because unfortunately it's not quite accessible. There's a couple of niggles that make that a little difficult to do, but if you know a little bit of trickery, and we've done some of it before, and in a previous video I've already pre-done it for this one just to save time. Because it's going to be a lot of reading anyway, but I've already enabled SSH on this machine. It wasn't enabled by default. And that gives us a whole lot more wiggle room, because if without SSH this task is undoable for blind screen reader users currently. Because it's once again a case of every file you need is locked into the machine, so if you can't access the machine, you're out of luck. But we had to make ourselves a door, and we're going to do the flag in a very different way today than the task describes, for a very simple reason. And we'll get to that when we do, but I've already done it. I've not filled it in yet, but I've already done my version of things, and I know it's going to work, so that's good. Yeah, let's just begin, because there's a lot of stuff here that we have to go through, and I have to read. So, little machine that wanted to learn. The story. Task banner for day 14. We don't get to know what's on it. The CTO has made our toy pipeline go wrong. By infecting elves at key positions in the toy making process, he has poisoned the pipeline and caused the elves to make defective toys. Oh no, broken toys. McSkitty has started to combat the problem by placing control elves in the pipeline. Control elves. I think we're having a case of English is not the first language here today. It's kind of amusing. These elves take measurements of the toys to try and narrow down the exact location of problematic elves in the pipeline by comparing the measurements of defective and perfect toys. However, this is an incredibly tedious and lengthy process, so he's looking to use machine learning to optimize it. And before I continue, I'm going to close my Discord because it keeps going off. There. Learning objectives. What is machine learning? Basic machine learning structures and algorithms. Using neural networks to predict defective toys. Accessing the machine. Before moving forward, review the questions in the connection card shown below. Oh, there it is. Last few times I looked at this, there was no connection card, but now it's here. What should I do today? Connection card details. Start the target machine. A split screen view of him is available on the target. There is no direct stuff, but we have made ourselves a door, so it's fine. To access the machine that you are going to be working on, click on the green Start Machine button located in the top right of this task. After waiting 3 minutes, the VM will open on the right-hand side. If you cannot see the machine, press the blue Show Split View button at the top of the room. Return to this task. We will be using the machine later. Will we though? I mean, it's holding our files for us and it's going to run our code. But yeah, apart from that, we're not going to be doing much with the machine today. We're going to see. Oh, headings. Cool. I see headings for the introduction. Very well done, whoever this is. Introduction. Over the last decade, there has been a massive boom in artificial intelligence, AI, and machine learning, ML, systems. Just in the last couple of years, the release of ChatGPT has taken the world by storm. However, how these systems actually work is often shrouded in mystery, leading to a lot of snake oil sales tactics. In this task, we'll provide you with a glimpse into the world of ML to help demystify this incredibly interesting topic. We will create our very own neural network that can be used to detect defective toys! Exclamation point! Heading 2, Zero to Hero on Artificial Intelligence. Before we can create our own AI, we need to learn some of the basics. First of all, let's discuss the two terms. The term AI is used in broad strokes out there in the world, often incorrectly. We have to be honest with ourselves. AI can't just be a bunch of if statements. A better term to use is machine learning. ML refers to the process used to create a system that can mimic the behavior we see in real life. This is because there is an intelligence in the real life and its structures. The field is incredibly broad, but here are a couple of popular examples. Genetic algorithms. This ML structure aims to mimic the process of natural selection and evolution. By using rounds of offspring and mutations based on the criteria provided, the structure aims to create the strongest children through survival of the fittest. Particle swarm. This ML structure aims to mimic the process of how birds flock and group together at specific points. By creating a swarm of particles, the structure aims to move all the particles to the optimal answers grouping point. Okay. Neural networks. This ML structure is by far the most popular and aims to mimic the process of how neurons work in the brain. These neurons receive various inputs that are then transformed before being sent to the next neuron. These neurons can then be trained to perform the correct transformations to provide the correct final answer. There are many more ML structures, but we'll stick to neural networks for this task, as they are significant amount of as they are the most popular, and while there is a significant amount of maths involved in implementing an ML structure, we'll be abstracting this information. If you want to learn more, you can start here. This is where I started, and then work your way up. Okay, what is that? Is that Data Quest? That is Amazon.com. Neural networks. Baby University. What? Neural networks for babies. Teach babies by Fairy Chris. Okay. Yeah, we'll look into that. Oh, no headings here for the learning styles. I'm going to turn my music down a tiny little bit. It's a bit loud. There you go. Learning styles. First on our list of ML basics to cover is the neural network's learning style. In order to train our neural networks, we need to decide how we'll teach it. While there are many different styles and subtle subsets of styles, we will only focus on the two main styles for now. Supervised learning. In this learning style, we guide the neural network to the answers we want it to provide. We ask the neural network to give us an answer and then provide it with feedback on how close it was to the correct answer. In this way, we are supervising the neural network as it learns. However, to use this learning style, we need a dataset where we know the correct answers. This is called a labeled dataset, as we have a label for what a correct answer should be, given the input. Unsupervised learning. In this learning style, we take a bit more of a hands-off approach and let the neural network do its own thing. While this sounds very strange, the main goal is to have the neural network identify interesting things. Humans are quite good at most classification tasks. For example, simply looking at an image and being able to tell what color it is. But if someone were to ask you, why is it that color, you would have a hard time explaining the reason. Humans can see up to 3 dimensions, whereas neural networks have the ability to work in far greater dimensions to see patterns. Unsupervised learning is often used to allow neural networks to learn interesting features that humans can't comprehend, that can be used for classification. A very popular example of this is the restricted Boltzmann machine. Have a look here at the weird features the neural network learned to classify different digits. Not right now, I'm sorry. For this task, we will focus on supervised learning. It's an easier learning style for learning the basics, including the basic network structure. Basic structure. Next on our list of ML basics to learn is the basic structure of a neural network. Sticking to the very basics of ML, a neural network consists of various different nodes, neurons, that are connected as shown in the animation below. We just have Lottie animation as the alt text and we don't get to know what's in the animation. How incredibly unkind. As shown in the animation, the neural network has three main layers. Input layer. This is the first layer of the nodes in the neural network. These nodes each receive a single data input that is then passed on to the hidden layer. This means that the number of nodes in this layer always matches the network's number of inputs or data parameters. For example, if our network takes the toy's length, width, and height, there will be 3 nodes in the input layer. Outer output layer. This is the last layer of nodes in the neural network. These nodes send the output from the network once it has been received from the hidden layer. Therefore, the number of nodes in this layer will always be the same as the network's number of outputs. For example, if our network outputs whether or not the toy is defective, we'll have 1 node in the output layer for either defective or not defective. We could also do it with 2 nodes, but we won't go into that here. Okay, hidden layer. This is the layer of nodes between the neural network's input and output layers. With a simple neural network, this will only be 1 layer of nodes. However, for additional learning opportunities, we could add more layers to create a deep neural network. This layer is where the neural network's main action takes place. Each node within the neural network's hidden layer receives multiple inputs from the nodes in the previous layer and will then transform their answers to multiple nodes in the next layer. Now that we understand the basic layout of the neural network, let's zoom in on one of the nodes in the hidden layer to see what it's actually doing. Another animation with the alt text Lottie animation. We don't know what it says. As mentioned before, we will simplify the maths quite a bit here. In essence, the node is receiving inputs from nodes in the previous layer, adding them together, and then sending the output onto the next layer of nodes. There is, however, a little bit more detail in this step that's important to note. Inputs are not directly added. Instead, they are multiplied by a weight value first. This helps the neural network decide which inputs should contribute more to the output than others. The addition's output is not directly transmitted out. Instead, the output is first entered into what is called an activation function. In essence, this decides if the neuron node will be active or not. It does this by ensuring that the output, no matter the input, will always be a decimal between 0 and 1, or between -1 and 1. Now that we understand is a big word here. I don't understand any of this. Well, I mostly get it, but it just seems really abstract to me still, so okay. Now that we understand the neural network's structure and how the layers and nodes within it work, let's dive into how the network is trained. There are 2 steps to training the network: the feed forward step and the back propagation step. Feed forward loop. The feed forward loop is how we send data through the network and get an answer on the other side. Once our network has been trained, this is the only step we perform. At this point, we stop training and simply want an answer from the network. To complete 1 round of the feed forward step, we have to perform the following: an animation which just says Lottie animation. 1. Normalize all of the inputs. To allow our neural network to decide which inputs are most important in helping it to decide the answers, we need to normalize them. As mentioned before, each node and the network tries to keep its answers between 0 and 1. If we have one input with a range of 0 and 50 and another with a range of 0 and 2, our network won't be able to properly consume the input. Therefore, we normalize the input first by adjusting them so that their ranges are all the same. In our example here, we could take the inputs with a 0 to 50 range and divide all of them by 25 to change the ranges to 0 to 2. 2. Feed the inputs to our nodes in the input layer. Once normalized, we can provide one data entry for each input node in our network. 3. Propagate the data through the network. At each node, we add all the inputs and run them through the activation function to get the node's output. This output then becomes the input for the next layer of nodes. We repeat this process until we get to our network's output layer. 4. Read the output from the network. At the output layer of the network, we receive the output from our nodes. The answer will be a decimal between 0 and 1, but for decision making, we'll round it to get a binary answer from each output node. Okay. Backpropagation. When we are training our network, the feed-forward loop is only half of the process. Once we receive the answers from our network, we need to tell it how close it was to the correct answer. This is a backpropagation step. Here we perform the following steps. An animation with the alt text Lottie animation, can't see what it says. Calculate the difference in received outputs versus expected outputs. As mentioned before, the activation function will provide a decimal answer between 0 and 1. Since we know that the answer has to be either 0 or 1, we can calculate the difference in the answer. This difference helps us how close the neural network was to the correct answer. Helps us gauge, I guess? Update the weights of the nodes. Using the difference calculated in the previous step, we can start to update the weights of each input to the nodes in the output layer. We won't dive too deep into this update process, as it often involves a bit of complex maths to decide to update should be made. Oh dear, maths. I hate maths. Nah, actually I like it. Propagate the difference back to the other layers. This is where the term backpropagation comes from. Once the weights of the nodes in the output layer have been updated, we can calculate what the difference would be for the previous nodes. Once again, this difference is then used to update the weights of the nodes in that layer, before being propagated backwards even more. We continue this process of backpropagation until the weights of the input layer have been updated. Once all the weights have been updated, we can run another sample of data through our network. We repeat this process with all our samples in order to train our network. Whew. More text, dataset splits. The last topic to cover before we can build our network is dataset splits. Let's use an analogy to explain this. Let's say your teacher constantly tells you that 1 plus 1 equals 2 and 2 plus 2 equals 4. But in the exam, your teacher asks you to calculate 3 plus 3. The question here is, have you just learned what the answer is, or did you learn the fundamental principles required to get to the answer? In short, you can overtrain yourself by learning the answers instead of learning the required principle itself. The same thing can happen with neural networks. Overtraining is a big problem with neural networks. We are training them with data where we know the answers, so it's possible for the network to simply learn the answers, not how to calculate the answer. To combat this, we need to validate that our neural network is learning the process and not the answers. This validation also tells us when we need to stop our learning process. To perform this validation, we have to split our dataset into 3 datasets below. Training data. This is our largest dataset. We use it to train the network. Usually this is... Oh. I don't know what that was. Usually, this is about 70 or 80% of the original dataset. Number 2 is validation data. This dataset is used to validate the network's training. After each training round, not ground, we send this data through our network to determine its performance. If the performance starts to decline, we know we're starting to overtrain and would stop the process. Usually, this is about 10 to 15% of original data set. Now we have testing data. This data set is used to calculate the final performance of the network. The network won't see this data at all until we are done with the training process. Once training is complete, we send through the testing data set to testing data set to determine the performance of our network. Usually, this is about 10 to 15 of all the original data set. Wait. It was 70, 80, 10, 15, 10, 15. So I guess that's kind of makes 100%. Now you know how a basic neural network works, so it's time to build our own. Putting it all together. Now this is where the fun start begins. Now that we've covered the basics, we are ready to build our very own neural network. Start the machine in the top right corner. It will show in split screen after 2 minutes. You can find the files that you will be working with on the desktop in the neural network folder. You are provided with the following files. Detector.py. This is a script where we will build our neural network. Some of the sections have already been completed for you. Dataset train.csv. This is our training dataset. In this dataset, the events have not only captured the measurements of the toys for you, but also whether the toy was defective or not. We will use this dataset to train, validate, then test our neural network model. And we have dataset test.csv. This is your testing dataset. In this dataset, the elves have only captured the measurements of the toys. Due to the sheer volume of the toy pipeline, they were unable to determine if the toy was defective or not. Once we have trained our neural network, we will predict which of the entries in the file are defective toys for McSkitty to remove from the pipeline. Our first step is to complete the detector.py script. Let's work through the initial code. It has already been added for you in the script, as shown in the snippet below. There's a whole bunch of code here. I'm not going to read it out loud, but I'll have a snippet of the code being read by the computer.
Speech mode talk. Numpy is a powerful array and matrix library used to format our data. Import numpy as NP. Import number pandas is a data processing library that also allows for reading and formatting data structures. Import number is will be used to split our data. From splur number is used to normalize our data. From splur.preprocessing import standard scalar. Number is used to encode our text data to integers. From splur.preprocessing import label encoder. Number is our multi-layer perceptron neural network. From blank. Number these are the color labels that we will convert to int. Colors equals red. Blank. Number reads the training and testing data files. Training data equals page.red.csv. Training dataset.csv.
Read CSV training dataset. So yeah, in the in instructions it says dataset training, and in the code it says training dataset, which is kind of interesting. I think this one could have gone through like a final round of editing before going live, but okay.
Training data.head. Blank. Testing data equals page. Testing data.head. Blank. Number the neural network cannot take strings as input, therefore we will encode the strings as integers. Encoder equals label encoder. Encoder.fit. Training data color scheme. Training data color scheme equals encoder.transform. Testing data color scheme equals encoder.blank. Number read our training data from the CSV.
Yeah, so a whole bunch of code. I'm just going to scroll to the bit where... Yeah, let's see how we read the labels, because actually I saw some when I looked into this code earlier. There we go. Yeah, checker elf, blah, blah, blah. Let's work through what this code does. Okay. 1. The first few lines are all the library imports that we need for our neural network. We'll make use of pandas to read our datasets in scikit-learn for building our neural network. Yeah. Next, we load the datasets. In our case, there is a training and testing dataset. While we have the labels for the training dataset, we don't have them for the testing dataset. So while we can perform supervised learning, we will only know our know our neural network's true performance once we have uploaded our predictions for review. Yeah, that predictions bit's going to be an interesting one. Once the data is loaded, we need to make sure that all the inputs are numerical values. One of our data types in the toy's color is the toy's color scheme. In order to provide this data to our network, we will encode the colors to numbers. Lastly, we load the data. Variable X is used to store our training data set together with its labels stored in variable Y. Lastly, test X stores the testing data set that we will use to perform the predictions on. Okay. We'll now start to add the code required to build and train our neural network. We will do this in steps to perform the actions mentioned above. Before I do that, I'm going to actually grab these files and put them in a code editor, because at this point, I would much rather just have them on my own machine, honestly. So I'm going to be doing that. I'm going to be really quickly grabbing those files. We don't need that on the OBS. I don't think I'll just explain what I'll do. I have turned on SSH on this machine, so I can also use SCP, which essentially lets me copy files from the remote machine to the local machine. So I'm doing Ubuntu at 10.10.133.233 colon slash home slash Ubuntu slash desktop slash neural network, and we'll put that in the folder NN on my desktop. So I'm gonna do that. Does that work?
/home/ubuntu/desktop/neural network, not a regular file.
Oh, yeah, my bad. I forgot a flag.
Space caret n caret space n.
Make it NN.
Speech mode off.
And I'm going to, I forgot the recursive flag, because obviously that's a folder, not a file, so it's giving me an error message. So we'll just add the recursive flag, and there go the files. Yeah, I see them coming in. Then I'm going to open this whole project in Visual Studio Code, because I can do that now. And that is what we'll put on the screen for the moment. I'll put the detector file in there. There. Okay. The imports work. Yeah, I made sure I have a Python environment that has all these things in it, so my code editor won't go completely nuts. I'm going to switch that to my... I'm going to show that off real quick. I'll have to read everything on the text anyway, so it's pretty easier to just show code. There we goes. Okay, here's my code in my code editor of choice, Visual Studio Code. Let's continue. Creating the datasets. First, we need to create the datasets. In our case, we will use an 80-20 split. We will combine our validation and testing datasets, as we will use the completely new data for our testing dataset. To do this, we have to add the following line in our code after the insert dataset split code here line. Okay? Train underscore x, validate underscore x, train underscore y, validate equals y equals train underscore test underscore split, bracket x, y, test size 0.2. There we go. Now, I've already seen that this code is messy, because if we scroll down here, oh, it's fixed already in this one. Okay, so a previous version of these files had some syntax errors in here. Let's find that line.
Speech number is from slur, number is from slur, number is from slur, blank. Number, these are the color labels. The colors blank. Number reads the training and testing data. Training data equals page.red CSV. Training data blank. Testing data equals page.testing data blank. Number, the neural network cannot take string encoder.training data testing data color scheme. Training data color testing blank.
Yeah, looks good.
Number, read our training data from the CSV file. Number, first we read the data x equals np.assignary. Training data height, width, length, color
That's
scheme.
X.
Number, now we read the labels of our training data. Y equals
That's
np.assignary.
Y.
Number, read our testing data. Test x equals np.assignary. Testing
That's
data
test
blank.
X.
6 number insert insert dataset split code here 6 number.
And now we need
to split our training 6
put
number. Black print sample of our data. Black number. Now we need 6 number and number.
and now we put this line
train
here.
Number, train X,
like.
validate X.
So now we have more variables. Train X, validate X, train Y, and validate Y are now variables that have been made.
Speech mode off.
Very good. We can now continue with the next step. Yeah, it's done. Okay. This will split our training data set into two. X underscore train, actually train X, contains the training data, and validate X, I'm just going to read it the way it's meant to be read. Validate X are validation data. Train Y contains the labels for our training data, and validate Y are labels for validation data. Normalizing the data. Next, we need to normalize our data. We can do this by adding the following line in our code after the insert normalization code here line. Scalar equals standard scalar. Scalar.fit train X. That's not one line, it's a whole block, but okay. Let's see, how much do we need to copy? Yeah, train X equals scalar.transform train X. Test X equals scalar.transform test X. We're transferring all the things. Oh, this is too far. I'm going to copy this out. Find that line that I was talking about. Let's see. Here it is. Normalization code. Bloop. There it goes. That looks right to me. I'm a developer, but I don't do machine learning stuff, so I'm just taking this by storm as well here. As you can see from the lines of code, if you know how this reads, yes, we cannot cheat by determining the normalization on either the validation or test datasets. The normalization vector is only created from the train data, which is then applied to all three datasets, training the neural network. All right. Finally, we can train our neural network. First, we will create our classifier with the following code after the insert classifier code here line. Okay. Classifier is that whole thing. I'm not going to read all this code. I'm sorry. It's just too much of it. Oh, it's just one line. CLF equals MLP classifier bracket solver equals LBFGS in quotes. Alpha equals something. Hidden layer size equals 15. 2. Max iteration is 10,000. Okay, that's just one line. We can put that in. Push. There's that comment here. Insert classifier code here. We will do that. Here's your classifier code. All right, starting the training. Blah, blah, blah. What else? You can find more information on this specific classifier here. Okay, here's a bit of an explanation of what the values are doing. Solver equals, this is the algorithm used to update the weight. This is a classic back propagation algorithm, but others can be used as well. Okay. Alpha equals, quote, quote, the alpha value is used for the regularization of neural networks. We won't dive too deep into the math here, but we have selected a fairly default value. Okay. Hidden layer size. This tells us the structure of the hidden layers in our neural network. Based on the provided configuration, we will have 2 hidden layers with 15 nodes in each. Okay. Max iteration. This sets a cap on the number of iterations we can train our neural network before it is forcibly stopped. Next, we can train our classifier with the following code after the insert classifier training code here line. It's just clf.fit bracket train x train y. Okay, we can do that. Where's that comment here? Boop. When this step is complete, we have successfully trained our neural network. No, we've written the code to train our neural network. Validate our neural network. The next step is to validate our neural network. To do this, we can ask the network to predict the values based on the validating dataset with the following code added after the insert classifier validation prediction code here line. Another line. Y underscore predicted equals clf dot predict left bracket validate x. Okay. Where is that? Prediction code here. I appreciate all the comments. Tells me where I put stuff. Okay. Alright, what's next? As you will see, when you execute the script, predictions are significantly faster than training the network. This is why neural networks can actually be used in real-life applications, as the prediction rate is incredibly fast once the network has been trained. We can determine the accuracy of our classifier by comparing the two arrays with the following code. This function tests, okay, yeah. We have a loop, we do an if statement, we see if the validation and the predicted are the same. If so, then we add 1 to correct. If not, then we add 1 to incorrect. Training has been completed, blah, blah, blah. Okay. Accuracy equals blah, blah, blah. Okay, print equals blah, blah. As you will see when we run the code, the neural network is pretty accurate. Okay, we haven't done that yet. Finally, as a last step, we can now ask our neural network to make predictions on the testing data that was not labeled by the elves with the following code after the insert classifier testing prediction code here line. y.test predictions equals clf.predict test x. Okay, we'll add that in. And soon we'll have to switch our view again to probably a command line window because we're going to command line for a bit. Yeah, here's that if statement. I can see it. Everything is in here. We don't have to add anything there. That's good. That means we don't have to do more copy pasting. Yeah, insert classifier testing prediction code here. That goes there. Okay. This is it. We are finally ready to train and run our network. From the terminal, run the app. Okay. Wait a second here then. I'm gonna save this. I'm going to bring my this one. I'm going to copy paste this stuff back to where we were. So essentially what I'll have to do is make another neural network folder here and end on the desktop of this other thing, of this machine that we're not using, pretty much. And then we're going to copy everything that's currently in our NN folder to that folder. And once we've done that, we will we'll connect to over SSH. Oh, what's wrong? And then no such file directory. Oh, we have to make it first? That's annoying. Okay, give me a second then. Stop complaining. There it is.
Speech NN, no such file or directory. C users for NN greater SCPRNN.
I just made it.
C users for NN greater code dot. C users for
Oh.
C users for NN greater SCPRNN Ubuntu attend.
Wait, desktop and
users
yeah,
for NN.
that's fine. Oh, I'm dumb. I'm a dumb.
NN, no such file or directory.
We are in the NN folder, so I can't do it from there. If I do it now, it should work fine. Yes, it does. Very nice. Okay, we're going to connect to the SSH again, and then we're going to copy that, put the view on that, because we're going to have to do some fun stuff with this. There you go. I'm going to put my OBS to capture that window real quick. There it is. All right, so with everything went right, which I don't know if it did, honestly. We should now be able to go into here, go to the NN folder, and run that file that we just modified, python detector.py. Run like the wind. Oh,
Speech command Python from dev Python is Python 3.
oh sorry.
$/n$y. What T-A-O space.
Here.
Python 3 and open file detector.py. Air no 2 no such file or directory. Ubuntu try
What?
/desktop /nn $. NN Ubuntu try /desktop /nn. NN Ubuntu try.
Oh, that's rude. All right.
Ubuntu try
Well,
/desktop Ubuntu try.
there. It's running. It's running. It's doing its thing. It's doing its thing. It's doing its thing.
Sample of our data features 6.733.46 11.266 14 8 7.031.54 14.95 1 14 8.833.24 14 3 7 14 defective 0 0 0 sample of our data after normalization features 0.1
He made a typo.
starting to train in our neural network blank bottom blank.
Okay, we are now waiting for it to train. It's training. Train. Now, once the training is done, we should be able to do some hackery, because I'm gonna tell you, like, while this is happening, while this is training, this is going to render a predictions.txt file. And the idea is that we're going to be posting that to what is literally predictions website.thm. And the idea is that you go to that on the browser of the machine that we're currently on. Now, obviously, given that we have a accessibility issue on that machine, we're not going to be able to be doing that. So that's unfortunate. Nothing to be done. Let's see how we did. Accuracy 91.35%. That should be a passing grade, so I'm going to take that as a huzzah, we did it. I will read the remainder of the little text that says here, and then once we go to the questions, we'll switch to the questions. But I'm first going to do what it says here. So this is the sample output that we had before. I'm just scripting through it real quick. Blah blah blah. Yep, still the output. Now we will predict. Yeah. Okay, these predicts will be saved. Okay. Predictions are saved. This file can now be uploaded to verify your neural network. Yeah. These predictions will be saved to a file. Upload your predictions here. HTTP website for predictions.thm under :8000 to see how well your neural network performed. If your accuracy is above 90%, you will be awarded with the flag, and McSkitty's toy pipeline will be saved. Okay, gotta switch back to the thing really quickly again, because there is more text. My, this is by far the most text in any of the tasks so far, I think. Here's the thing that I'm reading. Neural network accuracy. If your neural network is not able to reach 90% accuracy, run the script again to retrain the network and submit the new predictions. Usually, within 2 training rounds, you will be able to reach 90% accuracy on the testing data. This does, however, raise the question of why the neural network's accuracy fluctuates. The reason for this fluctuation is that neural networks have randomness built into them. The weights for each of the inputs to the nodes are randomized at the start, meaning that 2 neural networks are never exactly the same, similar to how different brains might learn the same data differently. To truly determine the accuracy of your neural network, you would have to train it several times and calculate the average accuracy across all networks. Several other factors might also influence the accuracy of the network. For example, the quality of the dataset. In machine learning, there is a term called GIGO, garbage in, garbage out. This term is meant to illustrate the AI isn't this magical thing that can fix every single problem. An ML structure is only as good as the quality of the data used to train it. Without good data, we wouldn't be able to receive any accurate output. Cybersec applications for machine learning. Machine learning, or AI as it's often called out there in the world, has real-life applications for cybersecurity. Here are just some of them. As shown in the example today, machine learning structures are incredible at finding complex patterns in data and performing predictions on large datasets with incredible accuracy. While humans can often do the same thing, the sheer amount of data and predictions required can be overwhelming. Furthermore, the intricate connections between different inputs cannot often be determined by a human, whereas ML structures can learn these decision boundaries in hyperspace, allowing for features to be connected in more than 3 dimensions. This can be used for classifications that are complex, such as whether network traffic is malicious or not. ML structures are incredibly good at anomaly detection. If you provide a well-trained ML structure with the thousands of data points, it will be able to discern the outliers for you. This can be used in security to detect anomalies such as unauthorized account logins. As ML structures have the ability to learn complex patterns, they can be used for authentication applications such as biometric authentication. ML structures can be used to predict whether a person's fingerprint or iris matches the template that has been stored to provide access to building or devices. CyberSec cautions for machine learning. While there are many benefits to AML in cybersecurity, caution should be observed for the following 2 reasons. This person really likes lists. Machine learning, just like humans, is inherently imperfect. There's a very good reason why the answer provided by the neural network is called a prediction. It's just that, a prediction. As you saw in today's example, while we can get incredibly accurate predictions from networks, it's impossible for 100% of the predictions to be correct. For this reason, we should remember that AI isn't the silver bullet for all problems. It will never be perfect, but it should be used in conjunction with humans to play to each of their strengths. And then the second one is the same power that allows machine learning to be used for defense means that it can also be used for offense. As we will show you in tomorrow's task, ML structures and AI can also be used to attack systems. We should, therefore, always consider this a potential threat to the systems we create. Whew. That was all text, and I'm wondering how accessible tomorrow's task will be if that's what we're going to be doing, but okay. What is the other term given for artificial intelligence, or the subset of AI meant to teach computers how humans think or nature works? I'm guessing they want machine learning for that one. They do. Very good. What ML structure aims to mimic the process of natural selection and evolution? Genetic algorithm. That is correct. Hooray. What is the name of the learning style that makes use of labeled data to train an ML structure? Supervised learning. What is the name for the layer between the input and output layer of neural network? Hidden layer. What is the name of the process used to provide feedback to the neural network on how close its prediction was? Shit. Validation? No. How many characters? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. What is the value of the flag? Okay, so the next one is the flag. What is the name of the process used to provide feedback to the neural network on how close its prediction was? Let's see. Find it. Supervised learning, and this says that we get neural network to the answers. Oh, back propagation. Okay. Is that it? Back propagation. It is. Nice. All right, so for the flag, we're going to switch back to my command line window here for the flag real quick, because the flag is a bit of a doozy. We can't get it by ourselves. Not easily, at least. There isn't... Actually, it's easier to hack the flag than to get the flag actually legitimately. So we're going to be doing that. Now, there's a couple things we can do here. Obviously, website.thm is not a thing because thm isn't a viable host. And this website apparently only works on the on this particular machine. That tells me as a web developer that there's probably a hosts entry somewhere that tells me what that is. So let's go take a look at the host file. We go nano etc hosts. And if we look at the second line here, we have website for presentation.thm goes to 127.0.0.1, which is just localhost, which tells me this machine is running that website. All right. That is a piece to the puzzle. Now, there's a couple ways we could find out where it is. When I initially did it, I just ran a find. And I didn't really get anywhere with that. So I just figured out, you know, we can just look at the processes. We can do a PS AUX. Oh, yeah, that works too. And at some point I saw that there was a Socketify Python process running. And I have seen that before. I've seen that in a Flask application. So I figured there's probably a Flask application on this machine running somewhere. And if it's, I looked in my user folder, I couldn't find it. So I decided, what if I check in the root folder? It's be a very bad idea to run this as root, but okay, that's what apparently they're doing, because that's where I found it. Like, I knew I had root access because I could start do sudo system control SSH start at the beginning to make sure the SSH thing was on. So I'm just going to go to root. Actually, I'm going to switch to root. It's easier. Oh, sudo su. There we go. We are now root. Now we're going to /root. And let's see what we have in here.
Checker hosting snap through the TryHackMe number.
Checker sounds like a promising thing. Let's have a look at that.
Through the TryHackMe. Main.py static templates testing answers.csv uploads through the TryHackMe.
Yeah, this really looks like a Flash application. So from that, I know that the templates are going to hold the HTML files for things.
Through the TryHackMe.
Let's see.
Index.html, score.html.
Score.html looks promising, but I already know that the score.html, if this is indeed Flask, it's going to pull it from the Python file. Now, I see only one Python file here. So I'm actually going to open that file up in Nano here to see if there's a variable that might look helpful. And if I scroll down a bunch here, oh, I see flag. Flag is insufficient score for flag, get above 90% accuracy. Okay, that's its default value. So I'm going to look for a little further down. If line equals false, answer to the append equals 0. Okay. Yep, looks good. KLJ, KLJ. I'm not sure what that's all about, but all right. Try. We're going to open the file. We're going to do a thing. Scan through the lines in the file. And then we're going to tally up the incorrects and the corrects for answers and answers. Yeah, so here we make sure that we have the right amounts of scores. And then a little bit below here, accuracy, if percentage greater than 90%, flag equals THM, neural networks are neat, exclamation point. Now that looks very flag-like. So, while we didn't use the website that's in the task, and we didn't get the payment and the instant gratification, I guess, of doing it the way that it was meant to be done, where we could see our score, what we did do was hack into this computer system, sorta, and grab the flag that way. So I'm going to paste it in here. So it's THM, all in caps, left brace, neural dot networks dot r dot need exclamation point right brace. All N's are capitalized. Everything else is not. And that's the right answer. Awesome. If you enjoyed this room, we invite you to join our Discord server for ongoing support, exclusive tips, and a community of peers to enhance your Advent of Cyber experience. Let's just say we did that. And with that, the task is completed. That was a long one. A lot of reading for yours truly. I will quickly, before I disappear again, switch back to the browser window so people can see the answers for a little bit. There you go. Don't know if anything scrolled into view. I can't really check that, but here you go. And that was it for today. This was a fun one. This was a very text-heavy one, but we managed it, and I'm going to be uploading this now, and I'm going to get some dinner. Everyone, I hope this was helpful. I hope it was interesting to see me do some coding as well. And see you in the next one. Goodbye.